These are Mrs. Mooney's YouTube video notes for accuracy, precision, and significant digits. Both precision and accuracy are important characteristics of measured values. Accuracy describes how well the measurement agrees with the real value, that is, the accepted value, as measured by competent experimenters. Accuracy depends upon a properly working measuring device. That is why many devices such as balances, scales, etc. must be calibrated, and proper technique used by the person making the measurement. Precision, on the other hand, describes the degree of exactness of a measurement. Precision depends upon the instrument used to make the measurement. Generally, the device that has the finest division on its scale produces the most precise measurement. Compare a graduated cylinder to a beaker. The graduated cylinder has divisions of 1 milliliter, so you could report volumes to the nearest half a milliliter. The beaker, however, has divisions of 50 milliliters, so you could only report volumes to the nearest 25 milliliter. The graduated cylinder gives more precise measurements. Which is a more precise measurement? 20 centimeters, 20.1 centimeters, or 201.25 centimeters? The answer would be 201.25 centimeters, because this measurement is precise to the nearest hundredth of a centimeter. In science, significant means measured, not important, as in the everyday use of the term. In physics, we work with measurements, using them in formulas, charts, and graphs to learn about the world around us. And we use something called significant figures to indicate a measure's precision. When using significant figures in measurements, there are rules that have to be followed. If you are just stating the number of significant figures in a measurement, there are 4 rules. The first one is pretty easy. If the number is not a 0, it is significant. So for an example, these measurements, 24.7 meters, 0.43 meters, 0.743 meters, and 714 meters each have 3 significant digits. Rules 2, 3, and 4 apply to zeros. Zeros are what typically give students the most difficulty. But if you just take a moment to think about it, it won't be that hard. Rule number 2 tells you that if a 0 is between 2 non-zero numbers, it is significant. So this 0 would be significant because it's in between 2 non-zero numbers. Likewise, these 2 zeros are significant because they're in between 2 non-zero numbers, and this 0 as well. So each of these measurements have 4 significant digits. Zeros at the beginning of a measurement are not significant. If you see zeros at the beginning of a measurement, just cross right through them. They are never significant. They're just holding the place of a measurement. So if you think about it, this measurement right here, 0.0071, really didn't start to until the 1/1000th position. This measurement here didn't even start till the 10th position. So this measurement, 0.0071, would have 2 significant digits. 0.42 has 2 significant digits, and 0.000099 has 2 significant digits. Zeros at the end of a measurement are only significant if there's a decimal point anywhere in the measurement. So for example, 43.00, these last 2 zeros would be significant because there's a decimal in the number. This 0 here at the end of the measurement, 1.010, is significant because there's a decimal. And it doesn't matter where the decimal is. As long as there's 1, the zeros at the end of the measurement are significant. This 0 here also significant because it's in between 2 non-zero numbers. So this measurement would have 4 significant digits. 43.00 would have 4 significant digits, and 0.9000 would also have 4 significant digits because the zeros, 3 zeros at the end, are significant because there's a decimal in the number, but the 0 at the beginning is never significant, so it would not be. Zeros at the end of the number, if there is no decimal, are not significant. So 300 only has one significant digit. 4,300 only has two significant digits. 7,210 only has three significant digits. When putting numbers into scientific notation, keep significant zeros only. The two zeros here at the end of the 3,500 are not significant because there is no decimal in the number. So if you put this number into scientific notation, drop the two non-significant zeros. 0.0050, the zeros at the beginning of the number are not significant, so drop them. The zero at the end of the measurement is significant because there's a decimal, so you would keep that zero when putting the number into scientific notation. Likewise, the zero here in between the two non-zero digits is significant, so keep it when putting the number into scientific notation. Pause the video for a moment and state the number of significant digits in each of the measurements below. Then turn the video back on to check your answers. Okay, the answers are in bold and in parentheses. Please check your answers. And if you still have questions on how to determine the number of significant digits in a measurement, please ask me about it first thing next class period. When calculating using measured data, your answers cannot be more precise than the least precise measurement. For example, suppose you calculated the volume of an object whose length, width, and height were 22.4 meters, 11.3 meters, and 5.2 meters respectively. The volume of this object, if you just do the simple calculation according to the formula, would be equal to 1,316.224 meters cubed. But since none of the original measurements were measured to the thousandth position, our answer cannot be precise to the thousandth position either. So there are rules to help us report our calculated answers to the correct number of significant figures. The rules for adding and subtracting are: just add or subtract the measurements, then round your answer to the same number of places past the decimal as any one of your original measurements that has the least amount of digits, significant digits, past its decimal. So for an example, if you were going to add these three measurements, you look back at your original measurements, look and see which measurement had the least number of significant figures past its decimal. And that would be the middle one. It has one digit past the decimal, so you would round your answer to one digit past its decimal. So 369.76 would round to 369.8. If we were adding these three measurements, you look back and you see which measurement has the least amount of significant figures past its decimal. This one has 1, 2, and 1 respectively. 1 being the least amount of significant figures past the decimal in any one of the original measurements, so we would round our answer to one digit past its decimal. So this would round to 79.2. Same thing for subtracting. Go ahead and subtract your original measurements, then look back and see which measurement had the least number of digits past the decimal. This one has 2, this one only has 1, 1 is the least, so you round the answer to 1 past its decimal. And here's another example. 14 grams has no digits past the decimal. The other ones have 2 and 3 digits past the decimal respectively. 0 digits past the decimal is the least amount, so our answer would have 0 digits past its decimal. For multiplication and division, you multiply or divide your measurements, then round your answer to the same number of significant digits in the whole number as the measurement you multiplied or divided that had the least amount of significant digits in its whole measurement. So for multiplication and division, you look at the entire number, not just what's after the decimal, as you would for addition and subtraction. So in this example, 7.55 has 3 significant figures, 0.34 only has 2 significant figures. So when you multiply and divide, you get, or when you multiply, you get 2.567 meters squared. Looking back, the measurement that had the least number of total significant figures is 2, so you round your answer to 2 significant figures total. You don't care what comes after the decimal. 35.2 divided by 60. This measurement has 3 significant figures. 60 only has 1 significant figure, so you would round your answer to only 1 significant figure. And this example here, 3 significant figures, 3 significant figures, 2 significant figures. Your answer then would need to be rounded to 2 significant figures total. And lastly, again, 3 significant figures, 2 significant figures, so your answer needs to have 2 significant figures. Pause the video for a minute and complete the following practice problems below by stating the number of significant digits in the measurements and then reporting the answers to the correct number of significant digits using the rules for calculations. Again, the answers are in bold and parentheses, so check your answers, and if you have any questions, please see me first thing at the next class period. Another thing to keep in mind is when you are performing mathematical calculations, units must be the same. For an example, you cannot add, subtract, multiply, or divide kilometers and meters. Your measurements must either all be in kilometers or all be in meters. You can't mix milliliters and liters. The units must all be the same, either all milliliters or all liters. Same thing with centimeters and kilometers. They all must be one or the other. Kilograms and grams, either all kilograms or all grams. You can multiply or divide, but not add or subtract different types of units. For an example, you can multiply 2 meters by 5 seconds, because these are 2 different types of measurements. This is a measurement of length. This is a measurement of time. So you would just multiply the numbers and multiply the units. Likewise, you can divide 6 kilograms by 3 meters, because these are 2 different types of measurements. Kilograms is a measurement of mass. Meters is a measurement of length. So you would just divide the numbers and then divide the units. If you are multiplying 2 centimeters by 2 centimeters, these are 2 measurements of length. So if you're measuring one type of quantity, length for example, the units must all be the same. And they are, centimeter and centimeter. So you just multiply the number and then multiply the unit. Some more examples. I cannot divide 5 meters by 100 centimeters. These are both measurements of length, so my units have to be the same. So I would convert 100 centimeters to its equivalent, 1 meter. Then I can divide 5 meters by 1 meter. The answer is 5. The units cancel out. A meter divided by a meter, it cancels out and you have no units. I can divide 5 meters by 2 kilograms, because these are 2 different types of measurements, length and mass. So you just divide the numbers and divide the units. And again here, 2 measurements of length, but they are of the same units, both meters, so it's fine. Multiply the numbers, multiply the units. And lastly, I cannot multiply 5 meters per second by 15 minutes, because I have 2 measurements of time here, but one is in seconds, the other in minutes, and I cannot mix units of the same type of quantity. So I would have to convert the 15 minutes into 900 seconds, and then I can multiply now the 5 meters per second times 900 seconds gives me numerically 4,500. Seconds cancel out, leaving me with a unit of meters. When you are taking measurements in a laboratory situation, you may want to compare your measured value to the true value, and the percent error formula will do this. The percent error formula is the percent error equals the absolute value of the observed value, which is what you measured, minus the accepted value, which is the true value, divided by the accepted value times 100. So for example, if you measured the speed of a cart to be 15.1 centimeters, the true speed of the cart was 15.5 centimeters per second, what would be your percent error? According to the formula, it would be 2.6%.